Greetings and welcome to this tranquil space where curiosity can linger and scientific exploration proceeds unhurried. This evening, we journey beyond our current era. We're venturing deep into the past, to a time when even the ground beneath us would appear utterly unrecognizable. This expedition takes us to an Earth from many hundreds of millions of years ago. It predates cities, oceans in their current form, and even a global map that aligns with our modern understanding. This is the narrative of Pangaea, a singular, colossal continent that once spanned a significant portion of the planet, encompassing nearly all of Earth's landmass in one continuous expanse. Many have encountered this name fleetingly, perhaps in school textbook illustrations, or referenced in subdued documentaries. However, scant attention is paid to envisioning its true reality. What sights would greet your eyes were you present? What sensations would accompany breathing its atmosphere? Imagine traversing a terrain devoid of recognizable borders, gazing upon a firmament not yet defined by the geography we now comprehend. To grasp this ancient world, one must first discard the mental map currently held. The Atlantic Ocean did not divide the Americas from Europe and Africa. No vast Pacific Ocean bisected the globe's center. Instead, there was an uninterrupted landmass. Had you been able to walk across it, you might have commenced your journey in what is now northern North America, then continued eastward, entering modern-day Europe and Asia without ever boarding a vessel. You could have turned south and moved into Africa and South America without ever seeing an ocean break the horizon. Only land extended further than any traveler could hope to trek in a lifetime, encircled by a single immense ocean that embraced it like a ring. This world, however, was far from quiet. It was not a place of profound stillness, frozen in deep time. The Earth has always been dynamic, and the age of Pangaea was no exception. Potent, unseen, yet relentless forces shifted beneath the surface. They drove continents together, fusing them into one. They sculpted mountains from the crust, cleaved deep valleys, and propelled volcanoes skyward to paint the atmosphere with fire and ash. Within the heart of this enormous land, life unfolded under conditions almost inconceivable to us. Distant from the ocean, the climate was severe. Lacking seas to transport moisture inland, vast arid zones existed where precipitation was rare. Summers could bring oppressive heat, while winters ushered in piercing cold. The seasons were intense, the air dry, and the sky seemed to stretch boundlessly, interrupted only by distant mountain ranges or the silhouettes of forests adapted to this challenging environment. Even so, life permeated every corner. Towering flora covered parts of the landscape, while in other areas, crimson deserts rolled towards the horizon. Unfamiliar creatures roamed the ground, peculiar reptiles, some exhibiting traits that foreshadowed the first mammals, and insects far larger than any you would encounter today. Earth was vibrant, yet it hosted a distinct kind of life, shaped by the unique conditions of this unified world. Perhaps the most striking characteristic of all was the absence of divisions. Today, we are accustomed to a planet segmented by oceans, but in the Pangaean era, no such barriers existed. A river originating in what we now call Asia could meander its way into what would become Europe without ever being obstructed by a sea. Forests might span regions that would one day be split into entirely separate continents. The same animal species could migrate freely from one extremity of the land to the other. It was one Earth, undivided. Its surface was open and interconnected in a manner almost impossible for us to conceive today. Yet despite its grandeur, Pangaea was never destined for permanence. The very forces that assembled it were perpetually at work. Even as they held it together, they were preparing to cleave it apart once more. Such is the nature of this planet. Continents drift, oceans expand and contract, mountains ascend and descend. But during its existence, Pangaea left enduring traces that are still evident, influencing the evolution of life and forging the deep foundations of the world we inhabit. Before we reach the moment Pangaea first began to fragment, we must delve even further back, to the forces that initially brought it into being. For to comprehend what it was like to inhabit that ancient continent, we first need to understand how the Earth consolidated into a single entity. The story commences not with a singular dramatic event, but with slow, continuous motion. Beneath our feet, the Earth's crust is fractured into immense plates that glide over the softer, hotter material below. This movement is gradual, measured in centimeters annually, but given sufficient time, it completely reshapes the planet's surface. Long before Pangaea, other supercontinents existed: Rodinia, Nuna, and others whose names are seldom spoken outside of geological academic circles. They coalesced, they fragmented, and their pieces drifted, setting the stage for Pangaea's emergence. Over hundreds of millions of years, smaller continents and island chains collided, merging into increasingly larger land masses. Each collision folded mountains into the sky, constructed long ranges of stone, and left profound scars in the crust. These ancient seams persist today, concealed within the bedrock beneath us. Slowly, these fragments fused until, at last, the Earth held only one vast land. The sheer scale of this is almost impossible to comprehend. Imagine standing in Pangaea's interior, thousands of kilometers from the nearest ocean. The air would have been different, the climate harsher. There would have been no familiar sensation of proximity to a coast, no scent of salt on the breeze. It was a world of vast interiors, of deep continental heartlands where seasons could become extreme and isolation was profound. And yet, this very isolation molded the living world. Insects increased in size, possibly due to higher atmospheric oxygen levels. Reptiles adapted to endure the dry heat of the interior, while in other regions near the coasts, early forests created verdant corridors for life to propagate. It was within this crucible of shifting climates and connected landscapes that many ancestors of future creatures, dinosaurs, mammals, and even early birds, would eventually arise. The land itself bore the marks of perpetual change. Volcanoes erupted, streaking the sky with ash that would settle into the soil. Rivers carved lengthy valleys, transporting minerals from the nascent mountains to the lowlands. Deserts expanded and receded with the seasons. It was a planet in motion, but one unified by a single colossal continent. And everywhere you looked, the evidence of that unity was etched in stone and sky. Even the winds must have felt different. On a modern Earth, oceans disrupt and redirect global air currents. But in Pangaea's time, the absence of those dividing seas meant that wind could sweep across thousands of kilometers with minimal interruption. Dust from inland deserts could have traveled all the way to the coastal fringes, delivering nutrients to distant forests. Storms might have traversed greater distances, unhindered by oceanic boundaries. The entire planet's climate was influenced by the simple fact that nearly all the land was concentrated in one place. And so, in this ancient world, every sunrise would have illuminated a horizon shaped by a single connected Earth. No distant continents to ponder, no hidden lands beyond vast oceans, just one world, whole and immense under the same sky. Before this single great landmass existed, Earth was a vastly different place. Hundreds of millions of years prior to Pangaea's assembly, the planet was a mosaic of smaller continents dispersed across the globe and slowly drifting over a deep primeval ocean. These land fragments did not remain stationary for long, at least not on geological timescales. They moved, as they always do, carried by the slow conveyor belts of tectonic plates. Mountains rose where they converged. Oceans opened when they diverged. Each transformation was measured not in days or years, but in millions of years. And yet, every subtle movement was another step toward the creation of a single, unified world. To understand how this occurred, we must envision the Earth during the late Paleozoic era, approximately 300 million years ago. By this period, several large continental blocks were already traversing the planet. Laurentia, which would become North America. Gondwana, encompassing the future landmasses of South America, Africa, Antarctica, Australia, and India. And smaller pieces like Baltica and Siberia. These were not yet joined, but they were on a slow collision course that would eventually bring them together in one colossal embrace. The process commenced with earlier supercontinents, long before Pangaea. There was Rodinia, which existed nearly 1 billion years ago. When it fragmented, it dispersed land fragments into new positions, only for them to later regroup into another supercontinent named Pannotia. That one was transient. It also fractured, but its pieces began to drift towards one another again. These recurring cycles of assembly and separation are part of what geologists term the supercontinent cycle, a natural rhythm of the Earth's crust, driven by tectonic plate movement. As these fragments drew nearer, the oceans between them diminished. The Reich Ocean, for instance, once lay between Laurussia, an early fusion of North America and parts of Europe, and Gondwana. Over millions of years, that ocean narrowed until it vanished entirely, crushed out of existence by the merging continents. When land encounters land, the collision is not gentle. Rocks crumple like paper under immense pressure. Entire mountain ranges emerge where two plates lock together. The Appalachian Mountains in North America and portions of the Atlas Mountains in Africa are vestiges of these ancient impacts, scars of collisions that help stitch Pangaea together. From above, the world during this time would have appeared strange. You would observe great land masses creeping toward one another, surrounded by an immense global ocean named Panthalassa. As the continents converged, island chains were swallowed, their volcanic peaks crushed between colliding plates. Shallow seas disappeared. The boundaries between one landmass and another blurred until, at last, all of them became one. But concurrently with this slow-motion collision, the climate was also shifting. Large ice sheets still clung to parts of Gondwana, particularly in regions that would one day become South America, Africa, and Antarctica. Evidence in the rocks, scratches left by ancient glaciers, indicates that even during Pangaea's assembly, the Earth oscillated between colder and warmer intervals. As the continents collided and sealed off smaller seas, ocean currents shifted, and the atmosphere began to adopt a new rhythm. These climatic changes were not merely background details. They shaped the living world. When continents crash together, they create vast new highlands, and mountains alter everything around them. They redirect wind. They trap moisture on one side while casting long rain shadows over the other. In the era before Pangaea fully formed, these shifting landscapes were already sculpting the trajectory of evolution, preparing the stage for the types of plants and animals that would flourish when the supercontinent finally materialized. If you could stand on Earth at this time, you would witness landscapes that felt familiar in some respects, yet alien in others. Vast stretches of lowland swamp covered parts of what would become North America and Europe. Towering forests of primitive trees spread across the horizon. These were the Carboniferous forests, so dense and humid that their decaying plant matter would one day form the coal seams we still extract today. The air was rich in oxygen, higher than what we breathe now, enabling some insects to attain enormous sizes. Dragonflies with wings nearly a meter across glided above those forests. Giant millipede-like arthropods crept along the forest floor. It was a world teeming with life, an Earth still experimenting with its potential. To the south, Gondwana presented a different picture. Much of it lay closer to the polar regions where glaciers carved across its surface. These frozen expanses bore no resemblance to the warm swamps near the equator. Yet they coexisted, part of a planet in transition. As the continents crept toward each other, climate zones shifted, pulling cold regions northward and pushing warm regions southward until finally they began to merge into a new global order. And then, over millions of years, the last major collisions began. Laurasia struck Gondwana, and mountain ranges buckled skyward. The smaller plates that once floated between them were caught and crushed. This was the moment Pangaea truly started to take shape. It was not a singular event, but a lengthy series of impacts and merges, each one propelling the planet closer to the world-spanning continent that would define an entire geological age. By the conclusion of this process, the Earth's map would have appeared strikingly simple. Nearly all the land on the planet sat fused into one vast expanse. Around it, Panthalassa stretched outward in every direction, a single global ocean that reached the edges of the horizon regardless of your position. Along one side of Pangaea, an inland sea known as the Paleotethys still lingered, a remnant of older oceans that had not yet fully closed. But even that would eventually recede, absorbed as the continents pressed more tightly together. And so the stage was set. The world had consolidated into a single piece. The last collisions had concluded. The mountains stood tall. Deserts were already beginning to form in the deep interior. And the climate was shifting into patterns that would shape life for millions of years to come. But this was merely the genesis of Pangaea's story. Now that the continents had converged, the world was poised to change in ways far more dramatic than the slow collisions that created it. With the continents locked together, Earth embarked upon one of the most remarkable chapters in its history. Pangaea was no longer a theoretical concept, it was a tangible reality. The protracted collisions that had drawn land masses across thousands of kilometers were finished, and the world now stood as a single unified continent enveloped by an immense ocean. It was an Earth devoid of today's familiar divisions, and its sheer magnitude would have reshaped every aspect of the planet's surface. Pangaea's formation was not simply the merging of continents, it was the transformation of the entire Earth system. Mountain ranges ascended where land had buckled during the collisions. Deep, crustal scars became sutures, welding the fragments into a single entity. These scars remain visible even now. Geologists still trace them across continents separated by oceans, evidence of places where, long ago, they were joined. The collision zones were violent. When plates collide, the crust folds and fractures. Heat accumulates as rock grinds against rock. Magma forces its way upward, feeding chains of volcanoes that can extend for thousands of kilometers. During Pangaea's birth, this process was relentless. The supercontinent's central regions were sculpted by the uplift of mountains that rivaled the scale of the modern Himalayas. These ranges would later erode, their peaks worn down by time, but in their prime, they signified the raw power of the planet's restless crust. Simultaneously, vast basins opened between these ranges. Rainwater and runoff from the newly formed mountains carved extensive river systems, traversing the supercontinent's interior. These rivers nourished wetlands and deltas that became some of the most fertile regions of their time. Fossils preserved in these ancient basins recount the story of lush ecosystems that thrived in the shadow of the recently built highlands. But Pangaea's formation also generated a new type of land, one Earth had never witnessed on such a scale. As the continents fused, the interior of this vast landmass receded further and further from the moderating influence of the sea. The outcome was a continental core so remote from the ocean that moisture from coastal regions rarely reached it. This gave rise to enormous deserts, some of which may have spanned thousands of kilometers. The great expanse of the supercontinent's center was a land of extremes, a place where searing summers and bitter winters prevailed, while Pangaea's edges, near the surrounding ocean, remained wetter and milder. This pattern of dry interiors and wetter coasts was one of Pangaea's defining characteristics. Even now, we can trace it in the rock record. Red beds, layers of iron-rich sediment formed in hot, arid conditions, are scattered across the continents that once constituted Pangaea. These rocks are the ancient imprints of the deserts that spread across its heart. Meanwhile, coal deposits formed in swampy, humid regions indicate that near its coasts, dense forests flourished under heavy rains carried inland from the sea. Pangaea's climate was not solely shaped by its size, but also by its position. During the peak of the supercontinent's existence, much of it straddled the equator. This meant vast tropical belts crossed its middle, bringing heat and seasonal monsoons to some regions, while its southern and northern extremities extended deep into polar latitudes. No other configuration of land in Earth's history has combined such an enormous range of climates on a single, connected continent. From frozen southern ice sheets to equatorial rainforests, all of it existed on one continuous piece of land. Life adapted to these extremes. In the warm, wet regions near the coasts, dense forests of seed ferns and towering conifer-like trees covered the land. Their roots stabilized the soil, while their leaves formed vast green canopies that trapped humidity. These forests hosted early reptiles, amphibians, and an array of invertebrates, including remarkably large insects. In the arid interior, life told a different tale. There, plants evolved strategies to conserve water, and animals adapted to prolonged periods of heat and scarcity. It was a world of survival where every adaptation was a response to the demands of an immense and unforgiving landscape. Pangaea's formation also altered the oceans. With nearly all of the land gathered in one place, the surrounding sea, known as Panthalassa, became the dominant global ocean. Its currents circled the supercontinent, redistributing heat across the planet. Meanwhile, along one edge of Pangaea, the shrinking Paleotethys Sea persisted, an isolated remnant of earlier oceans. This sea became a vital pathway for marine life, a sheltered environment where reefs and shallow water ecosystems thrived, even as the open ocean remained vast and deep. This arrangement of land and sea created powerful wind systems. Without the complex shapes of modern continents to impede their flow, global wind patterns became more direct and intense. Seasonal monsoons swept across parts of Pangaea, delivering heavy rains to some regions while leaving others in perpetual drought. Dust from the interior deserts may have traveled immense distances, carried by winds across thousands of kilometers before settling into coastal forests or even into the ocean. But perhaps the most profound outcome of Pangaea's formation was its influence on life's future. By uniting all the continents, Pangaea eliminated the barriers that had once separated ecosystems. Species that had evolved in isolation now came into contact with one another. Predators followed prey into new territories. Plants and animals spread into regions they could never have reached before. This mingling of life would shape evolutionary paths for millions of years. Fossils discovered today in places as disparate as South America, Africa, and India are often nearly identical. Proof that during Pangaea's age, the same species roamed lands now separated by entire oceans. Even as Pangaea stabilized, it was never truly at rest. Deep within the earth, the same forces that had assembled it continued to move. Heat accumulated beneath the crust, slowly weakening it in places. Faults formed, invisible at first, but these fractures would one day become the genesis points for the great breakup that would scatter the continents again. But for now, Pangaea stood whole, an extraordinary arrangement that dominated the Earth's surface and defined an era. To have walked across it then would have been to see the planet in a way no one can see it now. There was no distant coastline hidden beyond the horizon, no foreign continent awaiting across an ocean. There was only one world, vast and connected, bound by the same sky, the same winds, and the same restless heartbeat of the earth beneath it. And it was here, in this unified world, that the next great chapter of life's history would begin. With the earth consolidated into one colossal landmass, the concept of distance was forever transformed. No oceans divided one region from another. No isolated continent was separated by thousands of kilometers of open water. Pangaea was a single continuous world from one horizon to the next. The land stretched on, unbroken by the familiar boundaries that define our planet today. To grasp this, imagine standing somewhere near the center of that immense continent. You could walk in any direction for months and never perceive the glint of an ocean on the horizon. Instead, you would traverse plains so vast that the sky appeared larger than it does now. You would pass rivers that meandered across entire regions, weaving through landscapes devoid of borders. You would move from one climate to another, not because you had crossed an ocean, but because the land itself was so enormous, the weather shifted gradually over unimaginable distances. This was not a world of isolated ecosystems. In our modern age, oceans create natural barriers that segregate species, fostering unique forms of life on each continent. But on Pangaea, those barriers did not exist. Plants and animals could spread freely, crossing vast stretches of land without ever being halted by a sea. Fossils confirm this. Identical species have been found on continents now separated by thousands of kilometers of ocean. Reptiles that once inhabited what we now call South America also left their remains in Africa. Early plant species extended across regions that today are dispersed across the globe. Pangaea enabled life to move as if the entire world were one single, interconnected habitat. The absence of borders also altered the behavior of the land itself. Winds could travel farther, unimpeded by mountain chains or fragmented coastlines. Massive air currents swept across Pangaea, transporting heat and dust from the dry interior toward the coasts. Rainfall, conversely, struggled to reach the continent's heart. Moisture from the surrounding ocean would fall as rain along Pangaea's edges, nourishing dense forests and wetlands. But by the time the air reached the deep interior, it had little left to give. What remained were vast arid zones, deserts so expansive that they stretched further than the modern Sahara. These dry regions formed a stark contrast with the humid belts near the coast, rendering Pangaea a world of extremes. The rivers that traversed the supercontinent carried more than water. They were highways for life. Early amphibians followed them from one region to another, their movements guided by the steady flow of fresh water. Along their banks, strange forests of ancient conifers and seed ferns created verdant corridors that linked one part of Pangaea to the next. Some rivers were so long that in our era, their courses would span multiple continents. Yet in Pangaea, they were simply part of a single, boundless landscape. And there were mountains, enormous ranges born from the collisions that initially created Pangaea. These mountains rose where continents had once met head-on, their crumpled layers thrust toward the sky. Some of these ranges were immense, stretching across distances so vast that they bound the land together like seams. Over time, erosion wore them down, and rivers transported their sediments into the lowlands, enriching the soil and feeding vast floodplains. Traveling across this supercontinent would have entailed moving from one environment to another in a slow, steady progression. From humid coastal forests, you would transition into open savannas and grasslands. From there, you would enter deserts that seemed endless, their red sands broken only by rocky outcrops and the occasional winding river. Farther still, you might encounter forests once more, nourished by mountain rains that generated their own localized climates within the larger whole. Pangaea was unified, but it was never monotonous. Its sheer size allowed every type of landscape to coexist, all stitched together on one colossal piece of land. The absence of borders also shaped animal movement. Early reptiles, the ancestors of creatures that would one day dominate the planet, could traverse enormous distances across Pangaea without encountering an ocean. They spread across this vast land, adapting to its many environments. Some settled in the wetter coastal forests, while others learned to survive in the dry interior. This mobility enabled species to propagate quickly and widely, creating ecosystems that spanned much of the supercontinent. Even the sky must have felt different. On modern Earth, coastlines disrupt wind flow and create regional weather systems. On Pangaea, the land was so massive that weather could roll across it for thousands of kilometers without interruption. Storms that formed near the coasts might sweep deep inland, their rain diminishing until it was nothing but dry wind. Monsoons could reach staggering scales, with seasonal shifts that drenched one side of the continent, while leaving the other in crushing drought. Despite all of this, Pangaea was not an empty, silent place. It was alive. Primitive forests stretched across entire regions. Swamps near the coast teemed with amphibians and early reptiles. In the arid interior, tough, drought-resistant plants anchored the soil against the sweeping winds. While smaller animals darted between patches of shade, even in its harshest landscapes, life persisted, carried across the continent by its open, unbroken reach. If you could stand there and gaze around, it might have been overwhelming. No horizon was close enough to feel familiar. No ocean offered a natural edge to the world. Everything stretched outward in every direction, as though the planet itself had grown larger. That sense of scale would have defined daily life on Pangaea. Travel was slow, movement was vast, and even the sky seemed to match the land beneath it in its immensity. This was a world where everything was connected, where mountains, deserts, forests, and rivers were all part of a single continuous earth. It was this unity that gave Pangaea its power, It shaped the winds and the rains. It guided the spread of plants and animals, and it prepared the stage for the next great transformations in the history of our planet, when this vast, borderless land would begin to evolve and challenge every living thing that called it home. Although Pangaea was a continuous continent, it was far from uniform. Its fringes and its core could have been considered different worlds. Along the coasts, the surrounding ocean's influence shaped the terrain. Humidity from Panthalassa was carried inland by steady winds, nourishing lush forests and swamps, where life flourished abundantly. But the further you moved from those coasts, the less of that oceanic influence remained. Step by step, the verdant coastal regions faded, replaced first by open plains, and eventually by the stark, arid expanse of Pangaea's vast interior deserts. The coasts were zones of constant dynamism and vitality. Warm, shallow seas met the land in wide tidal flats and estuaries where the boundaries between land and water blurred. Here, amphibians lingered near rivers and wetlands. Early reptiles hunted in forests of towering conifers and seed ferns. Insects, some considerably larger than their modern counterparts, buzzed through the humid air. The climate in these regions was warm and wet, moderated by the nearby ocean, allowing ecosystems to thrive much like the tropical belts of our contemporary world. Fossils from these coastal zones revealed dense vegetation and an extraordinary diversity of species. Some areas likely resembled the mangrove swamps of the modern world, with tangled roots and sluggish waters teeming with early fish and invertebrates. Farther inland, yet still within reach of the ocean's moisture, sprawling river systems cut through the land, feeding broad floodplains. Plains where lush, verdant forests thrived would have represented the most habitable areas of Pangaea. These regions were rich in sustenance and shelter, characterized by consistent and predictable seasonal cycles. However, with each step inland from the coasts, one would draw closer to a vastly different landscape. Deep within Pangaea's interior, rainfall was scant. The sheer scale that united nearly all of Earth's landmass also imparted one of its most defining characteristics, a continental heartland so remote from the sea that it developed into a desert on a magnitude unparalleled by any modern terrain. These were not mere patches of sand as we conceive of deserts today. They were immense, stretching for thousands of kilometers, interrupted only by sporadic rocky uplands or isolated river systems. Geologists have unearthed evidence of these arid zones in the form of red beds, layers of iron-stained rock that signify hot, dry conditions. These rock formations reveal that much of Pangaea's inner expanse was a realm of relentless sun and minimal precipitation, where only the most resilient life forms could endure. In this interior, the air would have felt oppressive during daylight hours, with heat shimmering off the ground. At night, lacking the insulating cover of clouds or the proximity of oceans, temperatures would have plummeted dramatically, leaving the land cold beneath a sky ablaze with stars. It was a world of extremes, demanding unwavering resilience for survival. Vegetation here was sparse and tough, characterized by deep roots and leaves hardened against water loss. Small reptiles and early mammal-like creatures adapted to this environment by burrowing for refuge or becoming active during cooler periods to escape the scorching sun. Between these arid zones and the coastal forests lay transitional regions of grasslands and open woodlands, where the climate gradually shifted from wet to dry. These corridors likely served as crucial highways of life on Pangaea, enabling animals and plants to traverse various parts of the continent. Along these routes, species propagated across the supercontinent, generating the widespread fossil patterns that scientists now discover on continents currently separated by oceans. Meanwhile, the coastlines themselves were far from uniform. Some areas received consistent rainfall and supported dense, swampy forests, while others, situated in the rain shadows of colossal mountain ranges, were drier than their latitude might imply. Monsoonal winds, driven by Pangaea's immense size and the sun's seasonal shift, brought alternating periods of floods and droughts to specific coastal areas. The land was never static. Annually, storms swept inland, rivers swelled then receded, and forests adapted to cycles that persisted for millions of years. This stark contrast between the coasts and the interior influenced more than just the landscape. It also shaped the behavior of resident animals. Coastal regions, rich in food, supported a broader array of species. In the deserts, competition was fierce and life was highly specialized. Fossils indicate that creatures in these arid zones possessed unique adaptations, ranging from burrowing habits to specialized teeth suited for consuming tough, dry vegetation. Life was unevenly distributed across Pangaea, yet it remained interconnected. Rivers flowing from mountains to coasts, winds carrying dust from deserts to forests, and animal migration paths all linked these diverse environments. Even the air itself held traces of this interconnectedness. Dust storms originating from the interior deserts likely traveled vast distances, disseminating minerals across Pangaea and even into the surrounding ocean. This continuous movement of material forged a link between land and sea, fueling nutrient cycles that sustained both terrestrial and marine ecosystems. To journey across Pangaea would have been to traverse these sharp dichotomies, from the moist, teeming forests of the coast to the barren, sun-baked expanses of the deserts, and then back again as one approached another distant sea. It was a singular world, yet it encompassed climates and landscapes that today would be separated by oceans. This was the true magnitude of Pangaea, a land so vast it harbored its own extremes. And yet, despite these differences, this single supercontinent was neither a static nor a finished creation. Its mountains continued to shift, its climate evolved further, its deserts expanded and contracted, while its coastal regions transformed with the ebb and flow of ancient seas. It was a world in ceaseless motion, and that motion was far from concluded. The deeper one ventured into the core of Pangaea, the further the ocean's influence diminished. Moisture from the coasts simply couldn't penetrate this far. Winds lost their momentum, and the air grew increasingly dry under an unending sky. This was the vast interior, a land defined not by its abundance, but by its scarcity. Here, rain was a rare occurrence. Months could pass without a single storm, and when clouds finally did gather, their brief showers would vanish almost as quickly as they appeared, absorbed by the parched ground. This interior was monumental, stretching for thousands of kilometers in every direction. Modern deserts like the Sahara or the Gobi, while enormous, pale in comparison to the dry expanses that dominated Pangaea's center. Geologists studying ancient rock formations have uncovered successive layers of red sandstone, iron-stained and baked by heat, irrefutable proof of an arid world that persisted for millions of years. These layers depict a landscape sculpted by sun and wind, where rivers were scarce and lakes ephemeral, disappearing as soon-lived rains receded. The climate in this region was brutally harsh and relentless. During the day, the sun beat down mercilessly, without clouds to temper its glare. The ground would heat to the point where the air shimmered with rising thermal waves. At night, the temperature plummeted sharply. With no moisture to retain warmth, the land cooled rapidly, leaving the air frigid and thin beneath a vault of stars. Life in this environment had to conform to its severe rules or face extinction. While sparse, plants were not entirely absent in this interior. Low, resilient vegetation clung to the soil. Early conifers, seed ferns, and other drought-resistant species adapted to the perpetual struggle for water. Their roots, delving deep in search of moisture trapped far beneath the surface. Between these isolated pockets of green stretched wide plains of dry earth and rock, broken only by scattered dunes and the faint imprints of ancient riverbeds. These rivers, when they flowed at all, often ran only briefly before dissipating into the ground or evaporating under the unyielding sun. Animals that ventured here also bore the marks of adaptation. Many were small, their bodies designed to minimize water loss. Some burrowed deep underground, escaping the daytime heat and emerging only when the sun dipped low. Others congregated along the fringes of the few remaining rivers, subsisting on whatever water and vegetation they could find. Early mammal-like reptiles left their tracks in this land, alongside the footprints of smaller predators and the occasional larger herbivore that followed seasonal shifts in pursuit of better grazing grounds. The wind was a constant presence in the vast interior. Unimpeded by forests, it swept across the open land, carrying dust from one horizon to the next. Over millions of years, this dust deposited layers that remain preserved in the rock record. It would have been a world of subdued colors, reds and browns baked by the sun, pale skies that transitioned from dazzling blue to profound star-studded black, with little else to disrupt the monotony except the rugged profiles of distant mountains. Yet, this severity did not equate to lifelessness. Even in Pangaea's arid core, ecosystems persisted. Small oases formed where underground springs reached the surface. Seasonal floods from remote mountains carved temporary rivers through the parched landscape, drawing life from every direction. Fossils from these areas reveal sudden bursts of activity, indicating that for brief periods, these arid regions burst into life when water returned, only to fall silent again when the heat reclaimed them. The sheer size of this interior presented another challenge: isolation for its resident animals and plants. The distances were immense. Migration from one fertile region to another could span generations. Populations became highly specialized, shaped by the demands of the dry environment, until they no longer resembled their relatives from the coastal forests. This gradual process of adaptation was a primary driver of evolution in Pangaea's interior, yielding species capable of enduring conditions few others could survive. The wind-driven climate also reshaped the land over time. Without heavy rainfall, erosion progressed slowly. Rocky outcrops formed during Pangaea's genesis remained exposed for millions of years, their surfaces scoured but not obliterated. Sand, carried by constant gusts, sculpted dunes and carved intricate patterns into stone. These vestiges of ancient weather are preserved in the rocks we examine today, silent testaments to a world where the desert seemed endless. Despite its harshness, the vast interior was deeply interconnected with the rest of Pangaea. Dust from these dry lands drifted outward, carried by the wind into the wetter coastal regions, nourishing distant forests with minerals. Seasonal storms, though infrequent, sometimes formed along the interior's edges and swept outward, pushing dry air into greener lands and altering weather patterns far beyond the desert's immediate reach. In its own way, this empty expanse influenced the entire supercontinent, linking the destiny of its interior to its coast. To traverse the heart of Pangaea would have been to experience a silence almost unfathomable today. No sound of waves, no dense canopy of rustling leaves, only the sweep of air across stone and the occasional cry of an animal adapted to the emptiness. Yet, this silence was not devoid of meaning. It was here, in this great arid core, that life learned to withstand its most rigorous trials, preparing for the challenges awaiting in the evolving world to come. While Pangaea's core was characterized by dry winds and empty horizons, its periphery was sculpted by an entirely different force, the surrounding ocean. Panthalassa, the immense global sea bordering the supercontinent, stretched outwards endlessly in every direction, so vast that even from Pangaea's coasts, it must have appeared boundless. This singular ocean was more than just a backdrop. It was one of the most potent influences on the planet's climate, ecosystems, and the dissemination of life. Where land met sea, the world was transformed. Moisture carried inland by oceanic winds nourished the coastal regions, fostering belts of life significantly greener than the barren interior. These areas harbored rivers swollen by seasonal rains, wetlands teeming with primitive amphibians, and forests so dense they formed nearly unbroken canopies in certain areas. It was along these coasts that life flourished most abundantly, sustained by the constant interplay between land and water. The ocean itself was equally extraordinary. Panthalassa covered nearly 3/4 of the planet, its deep currents circulating slowly, but with immense reach. With only one massive continent to impede its flow, its waters moved in vast loops around Pangaea, distributing heat from the equator towards the poles. This consistent movement helped regulate the climate of the coasts, while leaving the interior lands to their extremes. Near the shorelines, however, Panthalassa's influence was immediate and palpable. Warm, shallow seas inundated low-lying regions along the continental margins. These shallow zones, sometimes extending for hundreds of kilometers, provided ideal conditions for life. Ancient reefs, constructed by early corals and sponges, rose from the seabed. Schools of primitive fish swam through clear waters, while trilobite-like arthropods, though nearing the end of their era, still persisted in isolated pockets. In these coastal waters, nutrient cycles interconnected the land and sea. Rivers from the interior transported sediments rich with minerals, nourishing the shallow marine ecosystems. These nutrients fueled plankton blooms, which in turn supported a burgeoning web of marine life. Fossils from these ancient seabeds narrate a story of abundance. Fish of many forms, invertebrates with intricate shells, and predators that patrolled the waters long before the first dinosaurs walked the earth. The coasts were also shaped by the ocean's temperament. Seasonal monsoons, driven by Pangaea's immense size, brought powerful storms to its edges. These rains replenished rivers and wetlands but also caused flooding, reshaping the landscape year after year. In some areas, these storms might have carried salt-laden air inland, leaving behind encrusted flats where water evaporated faster than it could accumulate. Each cycle etched another mark into the land, creating a coastline in perpetual flux. Despite the challenges of its interior, Pangaea's coasts were hubs of connection. They linked the land to the ocean and served as gateways for life between these two realms. Amphibians ventured into the wetlands to deposit their eggs, relying on the steady supply of fresh water. Reptiles followed, evolving traits that liberated them from dependence on aquatic reproduction, enabling them to move further inland. Even the first primitive ancestors of mammals likely emerged near these coasts, their survival intrinsically linked to the rich ecosystems spanning between the sea and the land. The air along these edges would have been teeming with life. Insects buzzed through forests bordering tidal flats. Early reptiles basked on sun-warmed rocks beside shallow lagoons. Primitive ferns and seed plants flourished in the humid climate, their roots clinging to the nutrient-rich soil washed down from distant mountains. Every segment of the coast vibrated with movement, and each season brought new growth, new migrations, and new struggles for survival. But just as the ocean gave life, it also drew clear lines of contrast. While the coasts were lush and dynamic, a mere few hundred kilometers inland, the greenery would dissipate. Rainfall diminished, and the air grew drier. The ocean's reach was powerful, but it was not boundless. The sharp gradient between fertile coastal zones and the arid interior was one of Pangaea's defining characteristics, a reminder that even on a world of connected land, the edges and the center operated by vastly different principles. The ocean itself, though seemingly constant, was far from still. Its tides and currents molded erosion along Pangaea's coasts, carving into cliffs and depositing sediments in novel locations. Some regions were submerged under shallow seas for millions of years before the water receded again. Others rose as the Earth's crust shifted, exposing once submerged sea floors to the air. This ceaseless interchange between land and sea created a dynamic map that compelled life to adapt repeatedly. Panthalassa was not the only ocean. Along Pangaea's eastern margin lay the Paleotethys Sea, a smaller yet equally significant body of water. It was within this relatively sheltered sea that many early marine species discovered stable habitats. Shallow waters, protected by extensive continental shelves, became cradles of evolution, fostering a diversity of creatures that would later spread into the larger ocean. This sea served as a counterpoint to Panthalassa's vast, open expanse, offering a tranquil refuge while the rest of the planet's waters churned in their immense, uninterrupted gyres. Standing on Pangaea's coastline, one would have seen no distant islands, no neighboring continents emerging from the waves, only the open ocean stretching to the horizon, an endless blue void encircling the Earth's single connected landmass. The sound of waves against the shore, the cries of primitive reptiles from nearby forests, and the steady winds sweeping inland would have underscored that this world was immense, unbroken, and perpetually in motion. The oceans at the planet's edge were more than just boundaries. They were the living, breathing skin of the Earth, binding water, air, and land into a unified system that established the rhythm for life. And from these coasts, the narrative of Pangaea would continue inward again, into the forests and plains that stretched between sea and desert, where the planet's unique and evolving life would take its next evolutionary steps. Pangaea's atmosphere was distinct from the air we breathe today. It was denser in some epochs, thinner in others, and its precise composition significantly influenced the creatures and plants inhabiting the world. To step outside and inhale during this ancient era would have been to draw in an atmosphere shaped by a planet in transition, one that bore the weight of its geological past and the potential for all that was yet to unfold. Evidence embedded in rock layers indicates that oxygen levels during certain periods of Pangaea's existence were higher than current levels. In the late Carboniferous period, just before Pangaea fully consolidated, oxygen might have constituted as much as 30% of the atmosphere, compared to today's 21%. This elevated oxygen profoundly altered everything. It fueled the growth of enormous insects and arthropods, creatures whose oxygen delivery relied on simple diffusion through their bodies. Dragonflies with wingspans exceeding a human arm soared over dense forests. Millipede-like invertebrates grew to lengths that would be astounding in any modern landscape. The air, quite literally, permitted them to become giants. Yet, the atmosphere did not remain constant. As Pangaea stabilized and transitioned into the Permian period, oxygen levels began to decrease. By the middle of that era, they may have dropped closer to 15%. Breathing under such conditions would be challenging for modern humans, but the animals of that time were perfectly adapted. Their lungs and circulatory systems had evolved to extract every bit of necessary oxygen from the thinning air. This atmospheric shift reshaped ecosystems, favoring species that could tolerate lower oxygen levels and gradually contributing to the decline of the oversized insects from earlier ages. Carbon dioxide also played a crucial role. Volcanic eruptions along Pangaea's fault lines released vast quantities of it into the atmosphere, warming the planet and energizing powerful weather systems. This greenhouse effect helped maintain the humidity and lushness of coastal forests, while in the vast interior, the heat merely intensified the aridity. The very chemistry of the air was intimately linked to the geology of the supercontinent, with each eruption and tectonic shift influencing life in ways discernible in the fossilized bones of surviving animals. For plants, this atmosphere presented both a challenge and an opportunity. High levels of carbon dioxide encouraged the growth of immense forests. Seed ferns, towering conifers, and other ancient plants thrived, their leaves absorbing the gas and releasing oxygen in return. These forests became colossal oxygen factories, nourishing the planet's atmosphere and stabilizing the climate. As they expanded along river valleys and coastal lands, they created pockets of breathable abundance in a world otherwise dominated by extremes. But the connection between air and life ran even deeper. Atmospheric circulation, the movement of air around Pangaea, was unlike anything on Earth today. With almost all the land concentrated into one colossal block, wind patterns became grander and simpler, sweeping unimpeded across thousands of kilometers. Warm air rose above the equator, generating powerful monsoons along the coasts, while cooler, dry air descended into the interior, feeding the sprawling deserts at Pangaea's center. The atmosphere itself functioned as an engine, and every living organism existed within its currents. Even the sky's color might have been subtly different. Higher concentrations of volcanic aerosols during periods of intense eruptions would have filled the air with fine particles, scattering sunlight and tinting the horizon. Some sunsets might have blazed a deep red, their glow extending across the flat, open lands of the interior. At other times, when the air cleared, the sky would have stretched in an unbroken blue arc, vast and sharp, with little moisture to soften it. Pangaea's breath also conveyed heat. Without the moderating influence of numerous smaller continents and oceans, seasonal temperature fluctuations were more extreme. Summers in the interior baked under hot, dry air, while winters cooled sharply, the air becoming thin and biting. Coastal regions experienced milder conditions, their air tempered by ocean breezes. Yet, even there, the rhythms of the supercontinent were felt. When the monsoon season arrived, humid winds swept ashore, feeding the forests with warm, moisture-laden air. When those winds shifted, dry air reclaimed the land. In this atmosphere, animals lived in synchronicity with the air they breathed. Some evolved efficient lungs to draw oxygen from a thinning sky. Others mastered stillness, conserving energy in the heat and dryness. Plants adjusted their leaf structures, their pores opening and closing to preserve water while still absorbing the gases needed for growth. Every adaptation was a direct response to the atmosphere, and every change in the atmosphere reverberated through the web of life. However, the most striking aspect of Pangaea's air was not merely its chemistry, but its expansive reach. A single atmosphere enveloped every corner of the supercontinent. Winds that originated in the deserts of the interior could sweep out to the coasts, carrying dust and minerals that would settle into distant soils. Moisture from the oceans could drift inland until it diminished and precipitated. Air connected the deserts to the forests, the mountains to the plains, and every living thing to every other. To stand on Pangaea and breathe would have been to inhale that entire world at once. The dry heat of its interior, the salt-tinged winds from its coasts, the faint traces of volcanic gases carried from far-off eruptions. Every breath was a reminder that on this unified continent, air was neither divided nor contained. It was the common thread that linked one end of the world to the other. And as the atmosphere shaped life, life, in turn, shaped the atmosphere, initiating a feedback loop that would define this era and prepare the planet for subsequent changes. For in Pangaea's air, heavy with history and dynamic with motion, lay the genesis of all that was to follow. The world of Pangaea was poised for its next great transformation. Its air, deserts, coasts, and forests had already set the stage, and now life itself was beginning to respond. This was the age preceding the dinosaurs, an era during which the forebears of future giants were taking their initial evolutionary steps. The Earth was not yet dominated by the towering creatures that would emerge later, but the foundations for their eventual reign were being subtly laid, one adaptation at a time. During the late Carboniferous and into the Permian periods, terrestrial life became more specialized. The coastal forests were dense, humid, and teeming with competition. Here, amphibians primarily inhabited rivers and swamps, their lives intricately tied to water. However, new arrivals, reptiles, began to appear. These creatures possessed a revolutionary advantage: the amniotic egg. Unlike amphibians, reptiles no longer needed to return to water for reproduction. Their eggs, protected by shells and membranes, could survive on dry land. This single adaptation unlocked access to Pangaea's interior, to the deserts and dry plains that amphibians could not reach. These early reptiles were not yet the colossal predators or towering herbivores of later ages. Many were small, agile, and low to the ground, feeding on insects and other small animals. But some began to grow larger. Among them were the synapsids, a group of creatures that would ultimately give rise to mammals. In the Permian, however, they were the dominant land animals, and their forms were as bizarre as they were diverse. Some, like Dimetrodon, bore enormous sails on their backs, possibly for thermoregulation or display. Others featured powerful jaws and robust bodies built for endurance, traversing the drier lands of the supercontinent in search of prey. In the forests and along riverbanks, herbivorous synapsids browsed on ferns and seed plants, their teeth adapted for grinding tough vegetation. They were stocky, slow-moving animals, but their size afforded them protection. In this world of vast landscapes and harsh climates, being large offered a distinct advantage, enabling them to travel greater distances for food, endure longer without water, and survive Pangaea's seasonal fluctuations. The insects of this era were still remarkably impressive. With oxygen levels higher in the earlier periods of Pangaea's history, some had achieved sizes that would seem impossible today. Dragonflies with wings nearly a meter across glided over rivers. Millipede-like arthropods stretched several feet in length, crawling across the forest floor. Although their prominence was beginning to wane as oxygen levels declined, they remained a defining feature of the landscape, reminders of a time when the very air had allowed life to attain astonishing proportions. In the ocean surrounding Pangaea, life was equally dynamic. Large predatory fish, armored with thick scales, hunted in the open waters. In the shallows, early sharks prowled, sleek and efficient, their lineage already well established along the coasts and in the smaller inland seas. Invertebrates like brachiopods, ammonites and crinoids populated the sea floor, filtering nutrients carried by Panthalassa's currents. The oceans were vast and deep, yet they were intrinsically linked to the rhythms of the land. Dust from Pangaea's deserts carried nutrients into the sea, and floods from coastal rivers replenished the continental shelves with minerals that sustained marine ecosystems. Back on land, the first major experiments in size were beginning to manifest. Among the synapsids and reptiles, forms emerged that hinted at what was to come. Some grew heavier and more imposing, pushing the boundaries of what the land could support. Their skeletons, preserved in stone, exhibit sturdy limbs designed to bear bulk and teeth adapted for a range of diets. These were not yet the colossal creatures of the later Triassic and Jurassic, but they were their forerunners. Evolution's initial attempts to populate Pangaea's enormous spaces with equally enormous beings. The supercontinent's climate propelled this process forward. In the lush coastal regions, food was plentiful. Forests produced layer upon layer of vegetation, allowing herbivores to feed almost continuously. In the arid interior, by contrast, survival favored endurance and size. Larger animals could travel greater distances for water and store energy more effectively. Over millions of years, these environmental pressures shaped the bodies of the creatures inhabiting these regions, setting the stage for the emergence of the great lineages to come. Predators followed suit. As herbivores grew larger, so too did the hunters that preyed upon them. Early reptilian predators, with long jaws and sharp teeth, evolved to match their quarry in strength and speed. These evolutionary arms races of size and power would persist into the Triassic, where they would give birth to the first true giants of the Mesozoic, the age of the dinosaurs. But even now, in this earlier period, the pattern was clear. Pangaea was a world that rewarded adaptation on a grand scale. The interconnectedness of the supercontinent also played a vital role. With no oceans to obstruct their path, species could spread across immense distances, carrying new traits from one region to another. A predator that evolved in one corner of Pangaea could, over time, follow its prey into entirely different climates. Herbivores could migrate from the wetter coasts to the drier interior, their populations diversifying and adapting to the unique conditions of each new region. Evolution did not occur in isolation here. It unfolded on a continental stage, and every movement of wind, every seasonal shift, and every geological change reverberated throughout that immense, connected system. And while the giants of the future had not yet arrived, the groundwork was firmly established. The forests were expanding, the deserts were waiting, the atmosphere was transforming, and in the quiet spaces between survival and adaptation, life was preparing to grow larger, stronger, and stranger than ever before. Across the vast expanses of Pangaea, the forests were unlike any we know today. They were more ancient, more peculiar, and composed of life forms that have long since vanished from Earth. These primeval woodlands served as the lungs of the supercontinent, influencing the atmosphere, anchoring the soil, and providing refuge for the burgeoning diversity of animals that roamed the land. To walk beneath their canopy would have been to enter a world both alien and familiar, a place where evolution was still experimenting with the fundamental components of future ecosystems. In the humid belts near the coasts, the forests were dense. Vast and sky-reaching, immense seed ferns, their fronds as wide as human arms, created thickets so dense that hardly any sunlight reached the ground. These plants, distinct from both true ferns and flowering trees, dominated expansive regions of Pangaea's landmass. Their stems and leaves formed widespread shady networks, beneath which smaller flora vied for every ray of light. In this low-lit, verdant realm, the air was saturated with moisture, and the earth was covered by deep layers of decaying plant matter, destined one day to become the coal seams buried far beneath today's continents. Towering over these seed ferns stood the primordial conifers. These were the forebears of contemporary pines, firs and spruces, yet during the Permian and Triassic periods, they were monumental pioneers. Their needle-like foliage allowed them to flourish across a broader spectrum of climates, from marshy lowlands to the drier, elevated areas bordering Pangaea's interior. Their sturdy, resin-rich wood supported trunks that ascended dramatically, forming vertical strata within the forest. Among these branches, small reptiles and early insects found sanctuary, their movements concealed by the ever-present canopy. Moving closer to the interior, where the climate became more severe and rainfall scarce, the forest gradually thinned. Here, drought-resistant plants prevailed, robust conifers, low-lying shrubs, and cycads with rigid, leathery leaves. These cycads, with their peculiar crown-like clusters of fronds, appeared to be vestiges of an ancient epoch. They prospered in locales where few other plants could establish themselves, stabilizing the soil and providing sustenance for the herbivores that ventured into the arid expanses between the forests and the immense deserts at Pangaea's heart. In certain areas, particularly near coastlines and river valleys, forests merged with extensive wetlands. These marshy environments were characterized by ancient horsetails and club mosses, plants that once achieved much greater heights than their modern counterparts. Their hollow, segmented stems formed thick stands along aquatic margins, their roots anchoring the earth against fluctuating currents. These wetlands served as vibrant nurseries for life, providing refuge for amphibians that required water for breeding, while early reptiles patrolled the fringes in pursuit of prey. Pangaea's forests were far from quiet. Insects filled the atmosphere with an incessant hum, their wings glinting in the fragmented sunlight. Giant dragonflies with their wings beating slowly skimmed over open areas and riverbanks. On the forest floor, millipede-like arthropods crawled through the deep leaf litter, while beetles and early ants commenced their silent work of decomposing plant material. Every sound and motion within these forests was an element of an intricate web that bound the entire ecosystem together. And where plant life was abundant, herbivores inevitably followed. Early synapsids and reptiles grazed among the ferns and cycads, their jaws adapted to process tough, fibrous vegetation. Some possessed stout, barrel-shaped bodies designed to accommodate powerful digestive systems capable of extracting maximum energy from Pangaea's hardy forest plants. Their tracks, preserved in stone, crisscross ancient floodplains once shaded by trees that have long since vanished. Even predators relied on these forests, though not directly for food. The dense vegetation offered concealment for ambush hunters. Smaller reptiles and early carnivorous synapsids prowled the shadows, their movements obscured by the layers of plants. The forest functioned as both a sanctuary and a hunting ground, a place where every leaf and branch contributed to survival. The air in these forests would have felt distinct from the dry winds of the interior, humid and heavy, carrying the aromas of resin, damp earth, and decaying plant matter. Sunlight penetrated in narrow beams, illuminating the forest floor in fleeting patches. In the coastal lowlands, fog occasionally drifted in from the ocean, enveloping the trees in a pale mist that persisted until the day's heat dissipated it. Further north and south, where the climate grew cooler, the forest transformed again. Conifers became more dominant, their evergreen needles adapted to endure regions where winters could bring frost. These forests were sparser than their equatorial counterparts, but demonstrated remarkable resilience, maintaining their presence even as the seasons cycled. Across all of Pangaea, the forests interconnected the land. They traced the paths of rivers deep into the interior, stretched along the coasts, and ascended the foothills of mountain ranges born from the continent's monumental collisions. They were not a singular, unbroken expanse, but rather a green network that unified the supercontinent, oxygenating its air and influencing the evolution of its diverse inhabitants. In due course, these forests would also become the stage for profound transformation. As climatic patterns shifted and Earth's atmosphere changed, the plant species that had governed Pangaea for millions of years would encounter new competitors. However, at this specific juncture, during the zenith of the supercontinent's existence, the forests stood at their peak, vast, untamed, and harboring the very first true foundations of the world that was yet to unfold. Life on Pangaea was articulated not just in its forests and deserts, but also in the creatures that traversed them. The supercontinent hosted an extraordinary spectrum of animals, ranging from the tiniest crawling insects to the pioneering robust reptiles destined one day to dominate the terrestrial realm. Each creature was an integral part of an evolving narrative of survival and adaptation, molded by the climate, the atmosphere, and Pangaea's boundless, interconnected geography. In the moist lowlands and coastal forests, insects reigned over both the undergrowth and the skies above. Elevated oxygen levels in earlier eras had propelled their diversification into forms significantly larger than most contemporary species. Dragonflies, with wingspans approaching a meter, glided gracefully between trees, their compound eyes fixed on prey they seized with swift, precise actions. Their flight was steady and powerful, a testament to how Pangaea's atmosphere had empowered these early aerial hunters. On the ground, gigantic millipede-like arthropods navigated the damp litter of decomposing plants. Some of these beings extended several feet in length, their numerous legs rippling in synchronized waves as they slowly traversed the shadowed forest floor. They were detritivores, consuming fallen leaves and rotting wood, fulfilling a crucial role in the recycling of nutrients back into the soil. Alongside them, beetles, primitive cockroaches, and early relatives of modern ants and termites formed vibrant micro-ecosystems within the dark spaces beneath the canopy. These insects were not merely background elements. They were the bedrock of Pangaea's terrestrial ecosystems. They fed on plants, broke down waste, and in turn served as food for the first small reptiles that had ventured beyond the swamps. This was a world in transition, where amphibians still congregated near rivers and wetlands, but reptiles were beginning to explore further inland, no longer dependent on water for reproduction. Their eggs, enclosed in protective shells, were pivotal to their newfound independence. Among these reptiles were early synapsids and diapsids, two lineages that would eventually give rise to turtles, lizards, snakes, crocodiles, and even dinosaurs. Yet, in the age of Pangaea, they remained small, wary creatures. They hunted insects among the roots of towering seed ferns or basked in the scattered patches of sunlight that pierced the forest canopy. Their limbs were robust, their bodies low and agile, perfectly suited for navigating the dense vegetation and uneven terrain of this ancient world. The synapsids, the group that would ultimately evolve into mammals, were also flourishing. Some were diminutive insectivores, quick and keen-eyed, darting through shadows in pursuit of their prey. Others, such as the early herbivorous synapsids, possessed barrel-shaped bodies and powerful jaws. They utilized their size both as a defense mechanism and as a tool for processing the fibrous plants that grew abundantly across Pangaea. They shared the forests with amphibians that had adapted to terrestrial life, but still returned to water for breeding, clinging to the last vestiges of a bygone era. In the wetlands and along the rivers, amphibians persisted as the dominant vertebrates. Some were small and nimble, their sleek skin enabling them to respire in both water and on land. Others were colossal, crocodile-like predators with broad jaws and sharp teeth, waiting motionless beneath the surface for an unsuspecting fish or reptile to approach. These amphibians were living relics of an earlier world, but in Pangaea's rich, waterlogged coastal environments, they managed to maintain their stronghold for millions of years. The interplay among these groups, amphibians, reptiles, synapsids, and insects, generated a complex web of life. In the coastal forests, insectivorous reptiles relied on the dense insect populations, while amphibians preyed on fish and smaller creatures in the swamps. Larger synapsid predators began to test their strength against the other inhabitants of this interconnected world. Fossilized trackways preserved in the rocks of ancient floodplains capture these moments. The zigzagging prints of small reptiles interspersed with the marks left by ponderous herbivores, often with the faint impressions of predators trailing behind. Further inland, within Pangaea's drier zones, reptiles emerged as the true pioneers. Unlike amphibians, they did not require standing water to survive, and they followed rivers and sparse vegetation deep into the continent's interior. Here, they developed tougher skin to conserve moisture, stronger limbs for traversing open terrain, and behaviors adapted to a harsher climate. These inland reptiles represent one of the earliest instances of life fully adjusting to Pangaea's arid core, where rainfall was scarce and the sun was relentless. Insects pursued them even into these regions. Hardy species capable of enduring heat and drought proliferated across the drylands. Termite-like insects may have begun to establish colonies, burrowing into the soil and wood to construct sheltered environments against the sun. In turn, the reptiles and early synapsids that hunted them evolved alongside their prey, their movements shaped by the shifting equilibrium between predator and food. Thus, Pangaea's forests, swamps, and deserts were linked not solely by the land itself, but by the continuous migration of life across it. Every plant sustained an insect, every insect nourished a reptile, and every predator carved out its niche in a landscape so immense that no single ecosystem existed in isolation. The absence of oceans separating these habitats meant that animals and plants could disperse far more easily than they can today, transforming Pangaea into a unified, interconnected stage where evolution unfolded on a continental scale. In this world, every creature participated in a grand experiment. The insects that grew large in the oxygen-rich air, the reptiles that severed their dependence on water, and the synapsids that lurked in the shadows were all components of a puzzle that would eventually give rise to Earth's future dominant species. For the time being, however, they were simply survivors of a world still striving for equilibrium, a world where the land was singular, the air was dense, and life was poised to make its next monumental leap forward. As life spread across Pangaea, one particular lineage of creatures began to acquire forms and characteristics that would ultimately lead to our own species. These were the synapsids, sometimes referred to as mammal-like reptiles, though in truth they were neither entirely reptilian nor fully mammalian. They constituted a transitional group, serving as a bridge between the cold-blooded hunters of ancient times and the warm-blooded animals destined to eventually dominate the planet. By the late Permian, synapsids were already among the most successful terrestrial animals. They manifested in diverse forms, from small, sharp-toothed insectivores to enormous, heavy-bodied herbivores that could rival the size of a modern rhinoceros. Their most distinguishing feature was a solitary opening behind each eye in their skull, an evolutionary modification that provided their jaw muscles with additional space for expansion. This seemingly minor difference granted them more powerful bites, swifter strikes, and more efficient feeding mechanisms than many of their reptilian adversaries. One of the most renowned early synapsids was Dimetrodon. With its elongated, sprawling body and the enormous sail protruding from its back, it appeared to be a creature born from pure imagination. That sail served a purpose beyond mere display. It may have facilitated thermoregulation, absorbing heat during cool mornings and dissipating it during the hottest hours of the day. In Pangaea's unpredictable climate, such an adaptation could mean the difference between life and death. However, not all synapsids were predators. Herbivorous forms, such as Adasaurus, featured smaller sails and broad, blunt teeth, adapted for grinding tough plant matter. These creatures moved deliberately across Pangaea's floodplains and forests, subsisting on cycads, ferns, and other resilient vegetation. Their physiques were designed for endurance rather than speed, and their sheer size helped deter smaller carnivores that lurked in their shadow. As the Permian period progressed, other synapsids emerged that exhibited traits more closely resembling those we associate with mammals. The therapsids, for example, began to display more advanced characteristics. Stronger limbs positioned more vertically beneath their bodies, differentiated teeth for cutting and chewing, and possibly even early indications of whiskers or hair-like structures, though direct evidence of the latter remains a subject of debate. These attributes conferred a distinct advantage. They were swifter, more efficient, and better suited to Pangaea's varied climates. Therapsids encompassed formidable predators such as gorgonopsids, sleek hunters equipped with long saber-like teeth and muscular builds. They were among the apex predators of their era, stalking the dry interior plains and river valleys of the supercontinent. Their skulls were more evolved than those of earlier synapsids, suggesting a shift toward quicker reflexes and heightened senses. In a world as vast and expansive as Pangaea, these adaptations enabled them to pursue prey over considerable distances and seize any opportunity to strike. Yet, alongside these predators were herbivorous therapsids, like dicynodonts. These stout, tusked creatures possess beak-like mouths for cropping vegetation and powerful jaws for grinding it down. Fossil evidence implies that some dicynodonts may have formed herds, migrating collectively across the landscape in search of food. Their capacity to thrive in both the wetter coastal regions and the drier interior enabled them to disperse across nearly every part of Pangaea, leaving their remains on continents that today are separated by oceans. What made these mammal-like creatures truly remarkable was their adaptability. They were not confined to a single environment or a singular mode of existence. Some prospered in the humid forests along the coasts, where plant life was abundant and water readily available. Others adapted to Pangaea's arid core, conserving energy and enduring prolonged periods without moisture. Their geographical range was so vast that they became one of the dominant life forms across the supercontinent. Their success also fundamentally reshaped the ecosystems surrounding them. As synapsids developed novel methods of feeding and hunting, they compelled their prey and competitors to adapt as well. This incessant evolutionary pressure fostered a dynamic, continuously changing world, where survival necessitated keeping pace with life's relentless arms race. In this manner, Pangaea's mammal-like creatures established the groundwork for many of the characteristics that would define their distant descendants. Warm-bloodedness, efficient locomotion, and intricate social behaviors. Even amid their ascendancy, however, the world around them was undergoing transformation. Volcanic eruptions spewed ash into the atmosphere. Tectonic forces strained the supercontinent, subtly altering its landscapes. The atmosphere itself fluctuated, its oxygen levels rising and falling. Through all these upheavals, the synapsids persevered. They were not yet mammals, but they carried the genetic blueprint of what mammals would ultimately become. To have stood on Pangaea and observed their movement across the land would have been to glimpse the nascent contours of a future still hundreds of millions of years away. Their powerful jaws, their sturdy limbs, and their ability to survive in a world of extremes marked them as the quiet architects of what was to come. They were neither the largest creatures in their world, nor the most terrifying, but they were among the most enduring. And endurance, in the harsh and restless age of Pangaea, was paramount. Beneath Pangaea's expansive surface, the earth was in perpetual motion. Its crust was locked in a ceaseless struggle with the forces emanating from below. Heat accumulated deep within the mantle, driving the slow but unyielding movement of tectonic plates. Along the boundaries where continents had merged, the ground buckled and fractured, and from those fissures fire erupted. Volcanoes represented the planet's heartbeat, and during Pangaea's era, their presence was ubiquitous. These volcanoes were not isolated peaks randomly dispersed across the land. Many arose along major fault lines where tectonic plates converged, forming chains that stretched for hundreds, even thousands of kilometers. In some locations, they erupted continuously, releasing rivers of lava that solidified into new rock. In others, their explosions were abrupt and devastating, propelling ash and gases high into the atmosphere, altering the climate for years at a time. Evidence of this geological activity remains visible today. Ancient lava flows, preserved in stone layers, delineate the outlines of long extinct volcanoes. Beds of volcanic ash lie buried within the rock record, silent witnesses to the ferocity of a world still in the process of formation. These eruptions were not infrequent occurrences. They constituted a regular aspect of life on a geologically active supercontinent. The impact of this volcanic activity on Pangaea was profound. Each eruption reshaped the land, sculpting new mountains and burying valleys beneath hardened basalt. Vast plateaus were created from successive layers of cooling lava, their surfaces subsequently eroded by wind and rain into rugged terrains. In the vicinity of these volcanic regions, soils enriched by mineral ash fostered new plant growth, forming pockets of fertile ground amidst otherwise harsh environments. Yet, volcanoes did more than simply sculpt the land. They transformed the atmosphere. Each eruption released immense quantities of gases into the air, including water vapor, carbon dioxide, and sulfur compounds. Carbon dioxide, in particular, acted as a potent greenhouse gas, trapping heat and intensifying the planet's already extreme climate. Over millions of years, these emissions played a crucial role in driving the temperature fluctuations that characterize Pangaea's environmental extremes. Sulfur gases, conversely, could exert an opposing effect in the short term. When powerful eruptions propelled sulfur aerosols high into the stratosphere, they reflected sunlight back into space, causing temporary surface cooling. These oscillations between volcanic warming and volcanic cooling resulted in a planet that was not only immense, but also volatile, its climate shifting with every significant eruption. Volcanoes also brought fire. Pangaea's forests, rich with resinous conifers and dense undergrowth, were susceptible to lightning strikes and, in some instances, to the heat and ashfall from proximate eruptions. Wildfires likely swept across extensive regions, incinerating old growth and paving the way for new plant life. In this manner, fire became an inherent part of the planet's cycle, reconfiguring ecosystems and creating mosaics of burnt land and fresh regrowth across the supercontinent. For the creatures of Pangaea, these eruptions and fires represented both peril and prospect. The ash clouds could obscure the sun, disrupting plant growth and compelling herbivores to migrate in search of sustenance. Predators followed in their wake, venturing into new territories made accessible by shifting vegetation. In other locations, volcanic activity generated fertile regions where life thrived. Lava fields cooled into rich soils that supported dense forests, and rivers, rerouted by eruptions, carved out new floodplains. One of the most dramatic testaments to this volcanic power occurred toward the conclusion of the Permian period, when colossal eruptions in what is now Siberia released enough gases to trigger profound alterations in the atmosphere and oceans. These eruptions, now known as the Siberian Traps, poured out lava over an area larger than most modern countries, sending shockwaves through Pangaea's ecosystems. Although this event marked the onset of one of Earth's most significant mass extinctions, it also underscored the deep interconnections between the planet's geology and its life. Even during less catastrophic times, volcanoes imparted a rhythm to Pangaea. Their eruptions marked the progression of ages, each layer of ash and lava a page in the planet's history. They served as reminders that beneath the forests, rivers, and deserts, the Earth was alive, a colossal engine of heat and pressure that never truly rested. To have stood on Pangaea during one of these eruptions would have been a humbling experience. Ash would have darkened the sky. Lightning, generated by volcanic plumes, would have flickered in the distance. The air would have carried the acrid scent of sulfur, while tremors rippled through the ground like the slow, steady respiration of the planet itself. And when the eruption subsided and the sky cleared, life would recommence, populating the land that fire had reshaped. In this way, volcanoes were not merely destructive. They were integral to the cycle that molded Pangaea, nourishing its forests, carving its mountains, and rewriting its landscapes. They gave the supercontinent its pulse, a profound, ceaseless rhythm that resonated through every corner of the ancient world. For millions of years, Pangaea existed as a single entity. Its mountains, deserts, and forests stretched from one horizon to the next, unified beneath a solitary sky. However, the identical forces that had forged it from disparate continents never ceased their motion. Deep beneath the surface, heat from the Earth's mantle exerted upward pressure, straining the junctures that held the supercontinent together. Slowly, almost imperceptibly, fissures began to develop. These cracks did not materialize all at once. Initially, they were merely rifts, elongated, narrow valleys where the crust extended and thinned under immense stress. In some places, magma ascended into these gaps, fueling chains of volcanoes that signaled the earliest indications of separation. Over millions of years, these rifts expanded. Where the land had once been solid and continuous, new basins started to form, hinting at the oceans that would eventually cleave Pangaea into the continents we recognize today. Geologists studying these ancient rift zones have discovered their enduring marks preserved in stone. In what are now eastern North America and western Africa, the rock strata bear witness to this gradual tearing apart. Ancient faults delineate the lines where the crust was pulled asunder, while thick deposits of basalt recount the story of magma welling up from profound depths. These features constitute the initial fingerprints of the Atlantic Ocean, though in Pangaea's era, the ocean itself was still millions of years from formation. The fragmentation of Pangaea was not a singular event, but a process that unfolded in distinct phases. Initially, the fissures were localized, confined to lengthy valleys that became filled with lakes and rivers. Over time, as the crust continued to stretch, these valleys deepened and volcanic activity intensified. Eventually, water from Panthalassa began to infiltrate the widening gaps. The Earth's singular unified landmass was commencing its fracture, its edges gradually yielding to the sea. As the landmass pulled apart, the climate shifted once more. Pangaea's interior, already arid, became even more isolated as rifts deepened and mountain ranges ascended along their margins. Meanwhile, the regions proximate to the expanding rift valleys experienced an increase in rainfall. Their lowlands transformed into fertile basins where rivers collected and forests flourished. Life adapted to these changes. Plants and animals that had once roamed freely across Pangaea now began to encounter the first genuine barriers in their world. Valleys, highlands, and expanding bodies of water that partitioned one population from another. The splitting of Pangaea also altered wind patterns. As the supercontinent's edges repositioned and new seas began to open, atmospheric currents adjusted in response. Moisture from the oceans reached previously unexposed regions, while other areas experienced increased desiccation. It was a slow, uneven progression, but it marked the commencement of the end for the singular, borderless world that had predominated for so long. Yet, even as the land fractured, life persisted in thriving. Early reptiles evolved into novel forms, some of which would give rise to the first true dinosaurs. Synapsids adapted to the fluctuating conditions, their descendants steadily approaching the characteristics of modern mammals. The forests expanded and contracted with the shifting climate, and the deserts continued to enlarge and shrink within the supercontinent's vast interior. The monumental breakup of Pangaea would not conclude for tens of millions of years, but its initial movements had already commenced. What had once been one world was slowly, steadily becoming many. The continents we identify today, North America, South America, Africa, Europe, and eventually Asia, were inscribed within those initial rifts, like a blueprint awaiting its unfolding. To have witnessed Pangaea during this epoch would have been to behold a land both familiar and unstable. The ground might have vibrated with distant volcanic activity. Rivers might have carved deeper into rift valleys that expanded slightly with each passing age. Mountains might have risen where the Earth's crust buckled under strain. It was a world in transition, its future continents quietly preparing to drift apart. And yet, even as Pangaea fractured, it was far from gone. For millions of years, the supercontinent would endure, its ecosystems adapting to every change. Life moved in concert with the land, populating every new valley and plain. But the initial fractures were there, expanding, and with them came the gradual reshaping of the Earth into the planet we recognize today. As Pangaea stretched and shifted under the slow, persistent pull of tectonic forces, its surface was interconnected not only by its landmass, but also by its rivers. These waterways were the lifeblood of the supercontinent, traversing thousands of kilometers, nurturing forests, carving valleys, and weaving together ecosystems from one extremity of the world to the other. Unlike today, where oceans segregate the grand river systems of each continent, Pangaea's rivers flowed across a single unbroken land. They acknowledged no boundaries, and their influence extended from the humid coasts to the arid core of the interior. Many of these rivers originated high in the mountains that had been formed by Pangaea's immense collisions. Snowmelt and rainfall at these elevated altitudes fueled torrents that incised deep into the rock, carrying with them minerals and sediments ground down over countless millennia. As they descended from the highlands, they broadened into sweeping rivers that meandered through the forests and plains, their waters gaining momentum as innumerable streams joined them along the way. These rivers became the vital arteries of the supercontinent, sustaining life in a world characterized by extremes. Along their banks, luxuriant vegetation flourished. Towering conifers and expansive seed ferns lined the floodplains, their roots securing the soil against erosion, while their fallen leaves enriched the ground with nutrients. Insects swarmed in these verdant corridors, their buzzing filling the air above the shallow backwaters, while amphibians sought refuge in the mud and reeds, preying on whatever they could capture. Small reptiles stalked the edges of these wetlands, hunting insects or darting into the water to evade larger predators. For Pangaea's animals, these rivers represented more than just water. They were crucial pathways. Herds of herbivorous synapsids followed their winding courses, feeding on the abundant vegetation that grew along their banks. Predators shadowed them, lurking within the cover of trees or lying in wait where the rivers narrowed, poised to strike. Over time, these waterways evolved into natural migration routes, linking distant regions of the supercontinent and enabling species to spread from one end of Pangaea to the other. The magnitude of these rivers was astonishing. In the vast interior, some may have flowed for thousands of kilometers before reaching their ultimate destination, either disappearing into immense inland basins or emptying into shallow coastal seas. Without oceans to divide the land, rivers could traverse what today would encompass multiple continents, crossing landscapes that range from humid forests to semi-arid plains, and eventually reaching the fringes of the deserts at Pangaea's core. When torrential rains arrived during the monsoon seasons, these rivers swelled far beyond their typical confines. Floodwaters inundated the floodplains, depositing rich layers of silt as they receded. These fertile soils supported dense plant life, attracting animals from every direction. Fossilized sediments from these ancient floodplains still bear the footprints of the creatures that once tracks of huge plant eaters, the impressions of predators' claws, and the delicate marks of smaller reptiles and insects were found there. Not every river on Pangaea flowed calmly. In certain regions, powerful, swift currents carved through steep valleys, eroding rock and moving vast quantities of sediment to lower elevations. These mighty rivers gouged out canyons and formed extensive alluvial fans, spreading out like fingers where they eventually lost speed. Each transformed the landscape over time, leaving behind a record of shifting waterways and vanished courses etched into the stone. Yet, even the quietest streams played a vital role. Within Pangaea's driest interior, small, seasonal rivers, ephemeral ribbons of water appearing only after rare storms, became crucial for survival. These short-lived floods left behind pools that sustained animals and plants long after the rains had ceased. Footprints, pressed into the drying mud, recount the story of creatures that came to drink, their paths converging at these temporary oases before disappearing back into the boundless desert. Beyond their immediate impact, Pangaea's rivers helped bind the supercontinent together in ways that extended far past their banks. The sediments they carried nurtured ecosystems hundreds of kilometers away. As minerals from the mountains settled across the plains, wind swept dust from the interior deserts into these waterways, only for it to be delivered to the coasts. Enriching the soils of distant forests, water linked Pangaea's extremes, its mountains, deserts, and coasts, into one enormous, interdependent system. For those who examine these ancient rivers today, the evidence is compelling. In the rocks of North America, Africa, and Europe, deposits of the same ancient river systems are preserved across continents now separated by oceans. Their patterns align, their sediments match, and their fossils tell the identical story. Once, long ago, these rivers traversed a single earth. To have stood on the edge of one of these rivers would have been to witness life teeming in abundance. Herds of herbivores crowded the shallows. Predators stalked the banks. Insects rose in swarms from the reeds, and amphibians slipped silently into the water. The air would have been thick with the scent of damp earth and vegetation, the sound of flowing water merging with the calls of distant animals. These rivers were more than just geographical features. They were the very lifeblood of a world yet undivided. And as Pangaea began to fracture and shift, its rivers too would transform, uprooted by the land's gradual upheaval. But for millions of years, they flowed without boundaries, uniting an entire supercontinent beneath their unending current. Above Pangaea, the sky was far from silent. It carried the supercontinent's voice, a language of wind, storms, and shifting air that molded the land below and the lives of everything upon it. To stand beneath that sky would have been to perceive a world in constant motion, its vastness filled not with stillness, but with an endless rhythm of weather sweeping from one horizon to the other without interruption. The winds constituted the initial and most consistent element of this soundscape. With nearly all the land gathered into a single mass, there were few obstructions to impede their flow. Air currents originating over the boundless expanse of Panthalassa could journey for thousands of kilometers across Pangaea before dissipating. In coastal regions, these winds arrived laden with moisture, rustling through forests and bending the crowns of towering conifers. Further inland, the same winds became thin and dry, hissing across the deserts, carrying dust and sand until the horizon blurred. In every corner of the supercontinent, the wind lent Pangaea its voice. During the monsoon seasons, That voice intensified. Warm air ascended from the heated land in Pangaea's interior, drawing in massive influxes of oceanic moisture. These monsoonal winds swept across the coast with heavy rains, drumming against the forests and swelling rivers until they spilled onto the floodplains. Insects filled the air in the ensuing damp heat, while amphibians and reptiles emerged from their hidden places to hunt and feed. For weeks, the sky vibrated with sound, the rush of wind, the roar of water, and the continuous patter of rain on leaves. But when the monsoons receded, silence returned to the interior. Dry season winds blew across the continent's heart, stripped of moisture, their currents sighing over dunes and rocky plains. In these moments, the sky above the desert must have appeared immense, a pale, cloudless dome, the air shimmering in the heat. At night, that same sky would have transformed into a canopy of cold brilliance, its quiet broken only by the faint whistle of wind between stones and the calls of creatures adapted to the dark. Storms contributed another voice to this ancient atmosphere. Given such immense distances and powerful wind patterns, thunderstorms could reach colossal sizes, their anvil clouds soaring high into the stratosphere. Lightning tore the sky in jagged flashes, followed by the deep rumble of thunder reverberating for miles across the open landscape. In the forests near the coasts, these storms would have unleashed torrential rains. In the arid interior, their clouds often passed without releasing more than a few drops, a stark reminder of how far Pangaea's heart lay from the ocean's reach. Volcanoes added their own sounds to the sky. Eruptions along the rift zones sent ash and gases high above the land, where the winds dispersed them across the supercontinent. These events sometimes turned day into twilight, shrouding the sun behind a grey haze when volcanic plumes interacted with the atmosphere. Lightning crackled within them, an eerie storm of fire and ash that must have echoed across the landscape for days. The sky also carried more subtle voices, the quiet air movements that shaped life in ways less dramatic but equally crucial. Gentle breezes spread plant spores and the seeds of the earliest conifers, carrying them far from their parent trees. Migrating animals followed the shifts in seasonal winds, their movements synchronized with the changing climate. Even the dust storms of the interior deserts served a purpose, lifting fine particles into the air and scattering them across forests and wetlands thousands of kilometers away, enriching the soil with minerals from distant lands. In this world, the sky was not merely a backdrop. It was an active component of Pangaea's living system, a conduit between the ocean and the land, between the deserts and the forests. Every change in temperature or pressure rippled outwards, affecting everything beneath it. Had you stood on the banks of one of Pangaea's great rivers and listened, you might have heard the hum of insects in the still air, the sigh of wind in the conifer branches, and in the distance, the low growl of thunder from a storm gathering far away. In the interior, you might have heard nothing but the dry rasp of air over sand, a silence so profound it was interrupted only by the sound of your own breathing. Near the coasts, the wind would have carried the smell of salt and the cries of creatures living where the forest met the sea. Day after day, season after season, this ancient sky inscribed its narrative across the land, shaping every climate and every living thing. It was not quiet, but it was unwavering, its rhythm older than mountains, older than rivers, older even than Pangaea itself. And though the continents would eventually separate, and new skies would form above them, the voice of that ancient atmosphere lingers still in the rock layers, in the fossilized remains of forests and deserts, and in the very patterns of wind that continue to encircle the Earth today. For millions of years, Pangaea flourished under its vast sky, its rivers, forests, deserts, and coasts, moulding a world filled with extraordinary life. But nothing on Earth remains static. The same planet that fosters life also challenges it. And during the late Permian, those challenges grew severe. It was an era of fire and silence when the planet's greatest extinction event occurred, almost completely depopulating Pangaea of its living inhabitants. The Permian Triassic extinction, frequently referred to as the Great Dying, was unprecedented. Around 252 million years ago, the Earth underwent violent upheaval. Enormous volcanic eruptions, most notably in the region now known as Siberia, released unimaginable quantities of lava and gas. For hundreds of thousands of years, these eruptions dramatically altered the atmosphere. Ash clouds obscured sunlight, while sulfur and carbon dioxide saturated the sky. The very air grew heavy with the exhalations of a world in crisis. Temperatures soared. Greenhouse gases from the eruptions trapped heat, propelling the planet into one of the warmest periods in its history. Pangaea's interior, already a land of extremes, became even more unforgiving. Rain grew scarce, rivers dried up, and the vast deserts expanded further than ever before. In the oceans surrounding the supercontinent, heat depleted oxygen, creating immense dead zones where life suffocated. The repercussions spread through every ecosystem. The luxuriant coastal forests withered. Many of the great synapsids, the dominant mammal-like reptiles of that epoch, vanished. Insects, which had thrived for hundreds of millions of years, experienced a sudden and catastrophic collapse, one of the few known mass extinctions in their history. Amphibians, once masters of Pangaea's waterways, dwindled as droughts and heat pushed them to the brink of survival. And yet, life did not cease. It never does. While most species perished, a few endured, clinging to the scattered refuges that remained. Some of the smaller synapsids, built for efficiency and survival, managed to weather the storm. Their compact bodies demanded less food and water, granting them an advantage in a world stripped of abundance. Early reptiles also persisted, especially those adapted to drier conditions. Their tough skin, robust lungs, and water-conserving physiology equipped them to outlast the surrounding chaos. In the oceans, though many fish and invertebrate species vanished, a few survivors adapted to the low oxygen waters, holding on until the seas gradually recovered. Even Pangaea's plants had their champions. The towering forests were reduced to remnants, but hardy conifers and drought-tolerant species endured, spreading anew once the skies began to clear. These survivors were not the largest or most dominant creatures of their era. They were the quiet, resilient ones, life forms capable of bending without breaking. The recovery was slow. For millions of years, the world remained scarred. Pangaea's once lush landscapes were sparse, dominated by small, tough plants and the scattered remnants of animals that had made it through. But from this silence, a new order began to emerge. The survivors diversified, filling the ecological voids left by the extinction. Small synapsids evolved into new forms, many nearing the characteristics that would one day define mammals. Reptiles, freed from their competitors, spread into new niches, setting the stage for the ascent of the first dinosaurs. The extinction reshaped Pangaea, not just in terms of life, but in the balance of its ecosystems. Where once the forests had been dense and the rivers teeming with amphibians and insects, the land now opened wide for the pioneers of the Triassic. These were creatures built for a harsher earth, descendants of the few that had endured the heat and hunger of the great dying. Their world was quieter, emptier, yet also full of opportunity. Even the sky would have appeared different after the catastrophe. Without vast forests to pump moisture into the air, rainfall patterns shifted. Dust from the desert spread farther. The air was thinner, drier, and often hazy, with the lingering traces of volcanic activity. It was a humbler world, but it was ready to begin again. In the silence that followed, evolution worked patiently. Pangaea's survivors were not the giants of its earlier ages, but they carried the seeds of what was to come. In their smallness, in their capacity to endure, they represented a new kind of life, one defined not by dominance, but by persistence. They would rebuild the supercontinent's ecosystems piece by piece, and in time, they would give rise to the next great chapter of Earth's history. The world had been broken, but it was not dead. Out of that stillness, new life would rise, and Pangaea, though altered, would remain the stage upon which it would happen. When the silence following the great dying began to recede, Pangaea stood as both a scarred and promising world. The supercontinent was stripped of much of its former abundance, yet its sheer scale and empty spaces offered something extraordinary, a new beginning. What survived would shape the future of life on Earth, and Pangaea's geography itself determined how that future would unfold. With nearly all land united into one immense mass, there were no oceans to isolate species. The survivors of the Permian extinction, small synapsids, resilient reptiles, and hardy plants, had a single, continuous stage upon which to proliferate. Populations could traverse vast distances without ever needing to cross a sea. This freedom of movement allowed life to intermingle in ways that would have been impossible on a divided planet. A creature that evolved in what is now South America could migrate northward into regions that would one day be North America, or even eastward toward areas that would later become Europe or Asia, leaving its descendants scattered across half the world. This interconnectedness accelerated evolution. When species met, they competed. When they competed, they adapted. Pangaea became a vast laboratory, a place where every climatic change, every topographical shift, and every new adaptation rippled outward, influencing life across the entire supercontinent. This explains why the Triassic period, which succeeded the Permian extinction, was an age of experimentation. The world was replete with ecological vacancies, and evolution rapidly moved to fill them. Small synapsids that had clung to the margins of the old world diversified into novel forms, some approaching what we would one day recognize as the earliest mammals. They remained small, primarily insectivores, scurrying through the undergrowth of Pangaea's recovering forests. Their size was not a disadvantage. In a land still recovering from disaster, smallness was a strength. It meant they required little food, could evade predators, and could exploit the countless overlooked niches within the supercontinent's ecosystems. Reptiles, too, seized this opportunity. Liberated from many of their competitors, they evolved into an astonishing variety of shapes and sizes. Some became swift, agile predators. Others grew bulkier, transforming into the first larger herbivorous reptiles that roamed Pangaea's plains and river valleys. Among them were the ancestors of the first true dinosaurs, still small and relatively inconspicuous at this stage, but bearing the potential to dominate the planet in future ages. Plants played an equally vital role in this new world. Pangaea's forests, though altered, spread anew across the coasts and river valleys. Conifers reclaimed the uplands. Their evergreen needles adapted to the seasonal fluctuations of the supercontinent's climate. Seed ferns and cycads took root in warmer regions, their robust forms feeding the burgeoning herbivore populations. Even Pangaea's dry interior supported patches of resilient vegetation, green oases that became stepping stones for life moving across the deserts. Pangaea's geography also influenced the planet's climate in ways that shaped evolution. Its vast interior remained dry and harsh, favoring animals and plants that could withstand extreme heat and drought. Along the coasts, where oceanic winds brought rain, ecosystems were more stable and abundant, supporting larger communities of flora and fauna. This stark contrast between the coasts and the interior ensured that no single type of life could prevail everywhere. Instead, evolution sculpted specialized solutions for every corner of the supercontinent. Even Pangaea's great rivers contributed to shaping its future. These waterways acted as corridors of life, connecting distant regions and allowing species to spread further than they otherwise could. In their floodplains, rich soils supported dense vegetation, and these green belts became highways for migration. Fossil evidence indicates that creatures living on opposite sides of Pangaea often shared striking similarities, proof that these river corridors linked the entire continent like threads in an enormous web. And yet, for all its unity, Pangaea also sowed the seeds of division. The first rift valleys that would eventually tear it apart were already beginning to form. These rifts created isolated habitats where populations of plants and animals became separated. Over millions of years, this isolation would lead to new species, each adapted to its unique environment, each carrying a piece of Pangaea's legacy. The supercontinent's influence would extend even further into the future. The animals that dispersed across it, those early reptiles, mammal-like synapsids, and the first true dinosaurs, would go on to dominate not just Pangaea, but the smaller continents that would later emerge when it finally fragmented. Its forests and deserts would shape the evolution of plant life that still has descendants today. Even its climate patterns would leave imprints in the geological record that scientists can still trace. A reminder of how profoundly this single landmass once controlled Earth's systems. To have stood on Pangaea during this time would have been to witness a world in the midst of transformation. The scars of the great dying were still visible, but life was returning, cautious at first, then unstoppable. The sound of wind through the conifers, the tracks of small reptiles in the riverbank mud, and the distant calls of predators were evidence of a planet rebuilding itself. Pangaea was more than a supercontinent. It was a crucible. From its extremes, its vastness, and its interconnectedness, it forged the foundations of the modern world. Everything that followed, from the rise of the dinosaurs to the first mammals, and eventually to us, was shaped in some way by the land and climate of this ancient unified Earth. For millions of years, Pangaea had been the focal point of everything. Its deserts, rivers, forests, and mountains stretched boundlessly beneath a single sky. Its life roaming freely across a land without borders. But even as it shaped Earth's future, the first deep fissures had already begun. Slowly, almost imperceptibly at first, the supercontinent that had united the world started to fragment. The process was not sudden. It unfolded over tens of millions of years, propelled by the same forces that had once drawn the continents together. Heat accumulated deep within the mantle, pressing upwards against the crust. Rifts opened, cleaving the land into vast valleys where lava welled up from Earth's interior. These rifts were the initial signs of separation, the earliest marks of the map we recognize today. In the regions that would one day become the Atlantic Ocean, cracks appeared between what is now North America and Africa. Initially, these were not oceans, but long, shallow basins dotted with lakes and rivers. Over time, they deepened. Water from Panthalassa slowly infiltrated, filling the rifts, and the first narrow seas were born. On the other side of Pangaea, the land that would become India, Australia, and Antarctica began to drift gradually away from Africa, pulled by the same tectonic forces. These changes reshaped not only the land but also the climate. As Pangaea fractured, new coastlines formed, bringing with them fresh sources of moisture. Regions that had once been arid began to receive rain from the expanding oceans. The great interior deserts, which had stretched unbroken across the supercontinent's heart, gradually diminished. Meanwhile, other areas grew drier, cut off from humid winds by rising mountain ranges or the changing positions of the drifting land masses. Life responded accordingly. Species that had once roamed freely across Pangaea found themselves divided by widening seas and growing rift valleys. Populations became isolated, separated from one another by geography for the first time in hundreds of millions of years. From this isolation, new species began to emerge. The ancestors of familiar lineages, dinosaurs, early mammals, and the first true crocodiles, evolved in these divided worlds, each group adapting to the new realities of a planet no longer whole. The breakup of Pangaea also altered the oceans. As the Atlantic broadened, it became a new conduit for currents that would eventually reshape the planet's climate. Panthalassa, once the single vast ocean surrounding Pangaea, now began to share its dominance with new seas that carved their way into the supercontinent. These changes would influence not only weather and rainfall, but also the migration of marine life, opening new habitats and closing others. On land, volcanic activity accompanied the slow separation. Along the rift zones, magma surged upward, creating vast lava flows and remaking the landscape. These eruptions released gases into the atmosphere, sometimes further warming the planet and driving dramatic climate swings. The land that had once been united under a single rhythm of wind and weather was now becoming a mosaic of smaller worlds, each with its own emerging character. For the creatures of this period, the changes were profound. Dinosaurs, which had first appeared when Pangaea was still intact, now began to spread across the drifting continents, adapting to the climates and landscapes that shifted as the land pulled apart. Early mammals followed similar paths, finding their own refuges in the forests and along the river valleys of these newly forming lands. What had once been one interconnected world was slowly splintering, setting the stage for the diversity that would define the Mesozoic era. If you could have stood on Pangaea during its prolonged farewell, you might not have noticed the change from one generation to the next. The land would have appeared solid, the forests would still have stretched to the horizon, and the rivers would have continued their ceaseless flow. But over millions of years, the cracks deepened, the seas widened, and the single great landmass was quietly transformed into the world of separate continents we know today. This was not an ending so much as a transition. Pangaea had provided life the opportunity to spread, to evolve, and to intermix in ways no other continental arrangement ever could. Its slow breakup did not erase that legacy. It carried it forward, distributing the descendants of Pangaea's creatures across new lands and new climates, where they would continue to change and adapt for millions of years to come. The supercontinent had begun its long goodbye, but its influence would resonate far beyond its own existence, inscribed into every ocean current, every mountain range, and every living thing that still walks the earth. Even though Pangaea is long gone, its presence has never truly departed from us. The continents we inhabit today, fractured by oceans and dispersed across the globe, are still shaped by its memory. Its mountains, its rivers, its deserts, and even the living organisms that traverse the earth all bear traces of that time when the world was unified. The echo of a single earth persists in the land beneath our feet and in the patterns of life that connect us to a much older history. You can discern this echo in the rocks themselves. The Appalachian Mountains of North America share their ancient origins with the mountains of Scotland and Morocco. Once, they were part of the same range, uplifted when Pangaea was formed, their peaks standing shoulder to shoulder before drifting apart. Today, they are separated by the Atlantic, yet their stone tells the same story, their layers still aligned like pieces of a puzzle pulled apart but never forgotten. You can also hear it in the fossils. Creatures that once roamed freely across the supercontinent left their bones scattered from one end of the world to the other. The identical species of early reptiles, the same plants, even the same insects appear in rock formations on continents now divided by entire oceans. Their remains are silent witnesses to a time when no sea stood between them, when the earth was a single, unbroken stage for life to unfold its narrative. Even the winds and waters still bear Pangaea's mark. The great ocean currents that circulate our planet today trace their beginnings to the initial openings of the Atlantic and Indian Oceans, born from the fractures that split the supercontinent. The monsoon patterns that drench South Asia and Africa are shaped in part by the positions of the drifting continents, remnants of movements that commenced when Pangaea first cracked and slowly separated. And life itself has not forgotten. The ancestors of mammals, dinosaurs, and countless other lineages were all molded by Pangaea's conditions. Its vast deserts hardened creatures to endure drought and heat. Its boundless forests sheltered small survivors who would one day become the first mammals. Its rivers and coastlines taught life to move, to spread, and to adapt to a planet where the rules of survival were constantly redefined by shifting climates and restless ground. Even within our own bodies, in the fundamental structure of our bones and the genetic memory inscribed in our cells, there is a link, an unbroken lineage that extends back through millions of years to that single, unified world. The echo of Pangaea is not merely a relic of the past. It is a force that continues to shape the present. Every mountain range that rises, every earthquake that shakes the ground, every drift of the continents beneath our feet is part of the same cycle that constructed and then broke apart that ancient world. We reside on a planet still in motion, still carrying the restless energy that once drew the continents together and then propelled them apart again. If you could stand on the highest peak today and gaze across the earth, you would perceive a world divided by oceans and continents. But if you look deeper, beneath the surface, beneath the lines we draw on maps, you would discover the same foundation, the same stone that once formed the floor of a single earth. And if you listen closely, in the slow grind of tectonic plates and the distant roar of the sea, you can still hear it, the low, steady echo of a world that was once whole. Pangaea is gone, but it is also omnipresent. It is in the mountains born of its collisions, in the creatures that evolved upon its soil, and in the quiet, ceaseless drift of the continents that will one day reassemble. The earth has not ceased moving, and as it rotates and shifts, it carries with it the memory of the time when all land was one, when every horizon was connected, and the sky arched unbroken above a single, boundless world. Thus, the story of Pangaea does not conclude with its disappearance. It lingers in every mountain range every current of wind, and every living thing that traces its lineage back to that ancient unified earth. We traverse land that was once conjoined, breathe air shaped by the forest that once covered it, and study fossils of creatures that roamed a world without borders. Pangaea reminds us that our planet has never been static. Continents drift, oceans open and close, climates shift, and life adapts. What was once one world became many, and in the distant future, those many worlds may one day converge again. The Earth is perpetually rewriting itself, and everything we observe around us is merely a chapter in a story that began long before us and will persist long after. If there is a lesson in Pangaea, it is that change is the constant, not the exception. Yet, within that change lies an unbroken thread, a connection that links the world we live in to the deep past. When we view a map of the modern Earth, with its scattered continents and vast oceans, it is easy to imagine distance and separation. But beneath those seas, in the slow movement of the crust and the shared history carved into stone, the Earth is still one. Pangaea was not just a place. It was a moment when the planet gathered itself into a single whole. And though that world has vanished, its echo is still with us, carried quietly in the ground beneath our feet and in the restless motion of the earth itself.